Hi, welcome to the Mentor and Engineer. Today we're going to be talking about Mohr's circle. Now Mohr's circle, you probably learned it in college, and well, it's just kind of a complicated issue, and I want to simplify that for how we're going to use it in the real world when calculating stress and strain. I want to make it simple and very user-friendly so that you are confident when you do use it that you are doing the right thing. So I'm going to give us an example today, and it's just going to be a cantilevered beam. So we're going to have a cantilevered beam here of length L, and we're going to apply force P. Now we're going to assume it's a uniform cross section and symmetrical top to bottom just to simplify things. So we'll be interested in this point right here and that point right there as far as what our stress and the strain is. Alright, now we're not going to use any units for this, not going to give it any forces, just going to solve it theoretically. Alright, so I can come up here with my normal stress is going to equal the moment times the distance to the centroid over the area moment of inertia, which in this case is going to equal P times L times C over I. And then we're going to have our shear stress, which is going to equal the force, the vertical force over the area. Alright, now we're going to graph these points on our plot here. It's kind of a unique plot. We're going to be plotting shear force against normal force, or normal force against shear force. Alright, and we're going to come up with 2 points right off the bat. And one of those is sigma and negative tau, and sigma and positive tau. Alright, the third point to plot our circle will most likely be this, because there won't be stress or strain in one of the directions. In this example, we're not pushing or pulling into the board, so there would not be any stress in those directions on our little cube there. So what we end up with is we're going to draw a circle through this. And I don't want you to get caught up in how we're doing this. If we do have forces in the other direction, we'll calculate that a different way, and we'll show that later. Alright, so the points that we're really concerned with on this is this point right here, which I'm going to call the principal normal stress, and here, which is the principal tau stress, shear stress. Alright, the way we calculate these two things is very simple, and it'll be the same for everything we do here. Alright, the first one will be the principal stress, and that's going to equal 1/2 the normal stress plus or minus the square root of the normal stress squared plus 4 times the shear stress squared. And we got our closing brackets here. Alright, now if we are consistent in using positive values for our normal stress, which we do in this, alright, not worrying about whether or not it's tensile or compressive, we can know that we always need to add, and we can get rid of that. Alright, to find the principal shear stress, it's basically a simplified version of this equation. It's 1/2 times the normal stress squared, or the square root of the normal stress squared, plus 4 times the shear stress squared. Alright, now it's very important that when we're doing this, we use both equations. We always have to calculate both equations. In this case, our limiting factor is going to be this top equation where the principal shear stress will be more, just because of the nature of it's a bending beam. Alright, so our bending stress or normal stress is going to be a higher component here. Alright, and in most cases, the bending stress will be so much more than the shear stress that we wouldn't even necessarily calculate the shear stress in there. It's such an insignificant factor. You know, it might add 300 psi or something of that nature. So a lot of times we'll just leave that out. However, if this was a beam that was in bending and torsion as well, we're putting a torsional member in here, moment in there, this number might be a lot higher, and it could even exceed the bending stress. Alright, now one final thing, when calculating our design factors, we can take our material strength and just divide it by the principal shear strength here and get a design factor. with the shear stress, it's a little bit different. So we're going to take our material strength and we're going to multiply it by a factor, which is the square root of 3 over 3, and that is actually equal to 0.577. All right, and then we're going to divide that by our principal shear stress, and that'll equal our design factor. All right, now this comes from the shear, distortion, max distortion energy theorem, and it is just a factor that has been empirically found to fit the data as far as how shear stress and normal stress relate when it comes to failing a material. Well, that's all I have on Mohr Circle for today. Please be sure to visit us in the future for more videos. Thank you.